welcome to this IChemE Global Awards 2021 webinar. My name is Mara Kefalopoulou and I'm your host for today's presentations. The IChemE Global Awards celebrate chemical process and biochemical engineering excellence and are widely considered as the world's most prestigious chemical engineering awards. Today we will be revealing the winner of the IChemE Young Industrialist Award, sponsored by Selfstealing Limited. This award recognizes the chemical engineer under 30 years of age who best demonstrates their achievements and tangible application of chemical engineering skills to address important technical, economic, environmental, or social issues. Our awards judging panel has been hard at work to review and rank all of the candidates, and here are our finalists. Sazeb Hassan from Pakistan Refinery, James Kenny from Dow Consumer Solutions, Bashir Aldekan from Saudi Aramco, Michael Turley from Shell, Donald Assander from Barden from PM Group, and finally Ed Ali Alalai from Saudi Aramco. All our finalists have been invited to join us today to tell us more about the work and answer your questions. You can get in touch using the GoToWebinar questions box on screen. So let's get started with our first finalist, and it's a pre-recorded video from Sazeb Hassan.
Hello everyone and welcome to today's session. My name is Shazib Hassan and I'm a chemical process engineer. First of all, I would like to thank IChemE for giving me this opportunity to present here. Let's start this presentation. I completed Masters in Chemical Engineering from NED University of Engineering Technology back in 2018 and Bachelor's from the same university back in 2014. During my Masters, I wrote a research article on the process system engineering analysis on process and optimization of the isomerization unit in Iranian Journal of Chemistry and Chemical Engineering. In the article, I explained how to find out the benzene content by looking at the temperature profile of reactor and how to analyze the deactivation of catalyst. Moreover, it discusses the optimization of stabilizer operation and impact of feed quality on the performance of the unit as KPI. Professional experience. I started my career from operations and switched to process engineering department. I'm an executive process engineer in Pakistan Refinery Limited, currently looking after the crude distillation unit and utilities, but I have also a valuable process engineering experience of reformer, hydrotreater, and isomerization unit, which could be summarized as gasoline division. From normal routine work to major troubleshootings, plant startups, shutdowns, reactors, unloading, loading, planning, and regenerations. Uh, these all are the part of my job description. I'm a certified Aspen user as well as I'm skilled in handling different simulation softwares like Pro2, Aviva, Engineering Design, integration of historian and simulator, and working on DCS like Honeywell and Yokogawa. From safety point of view, uh, I am the Bosch IGC certified and I'm also trained in PSM and RVPSM tools elements. I'm lead auditor of ISO 9001 QMS and have been participating in internal audit team. I have a total 7.5 years of oil refinery experience. So for engineering licenses, yeah, I'm a chartered chemical engineer, which is the golden title of process engineering on the platform of IChemE, and chartered engineer from Engineering Council UK. In addition, I'm a professional engineer from Pakistan Engineering Council. It's been 2 years since I became a chartered engineer. Yeah, I've completed various certifications in process simulation and modeling, and also related to the process safety, like incident investigation techniques and some communication skills. Like I completed Chinese one, level one, and level two. Um, Coming to the volunteering work, I've been participating in various volunteering work, like I took part in Meet the Process Engineer series, as well as I posted in Engineering Council case study. At this moment, I'm working as an IPT assessor and IChemE process engineering mentor. I'm fond of writing technical articles, so I joined IACP, International Association of Certified Practicing Engineers magazine, as a technical writer. Moreover, I'm a IKE university guest speaker, attended many universities inside Pakistan for delivering lectures on process simulation engineering. Last but not the least, I act as an external supervisor for university undergraduate final year projects. As you can see the pictures on this slide of my volunteering work. So these are some pictures which I've taken during my tenure in Pakistan Refinery Limited, uh, capturing different activities on the plant and off the plant, and also some volunteering work or the sessions in the universities. So coming to the uh, engineering work, first of all, I'm going to discuss the one of my optimization work, which is related to the cooling tower. Most of you guys already know that, but we can save money of around 18,000 USD per year on a basin volume of 750 meter cube or cubic meter. These figures could be very depending on the size of the cooling tower. I've written this article in ICP also, and link is also shared on the slide. Primary focus of this activity is to reduce the blowdown and the chemical cost, of course. However, alkalinity have to be maintained within a range to avoid scaling. So next is the key process consideration for caustic treatment CTU. As we know that the caustic plays an important role in controlling the chlorides in the overhead drum, so its location and optimization is also necessary for avoid cooking in furnaces and high sodium level in the residue stream. So therefore, some important KPIs are discussed in this article as well, that what is the impact of adding the caustic at the desalter downstream, and its result in the overhead chlorides form. So this is also an interesting article, and I would recommend to the audience to read this article as well. Okay, so next I'm going to share more of my work related to the simulation and modeling and the commissioning experience. Like a new boiler commissioning was carried out, and my task to handle the safe operation and to verify the process parameters given by OEM. So I developed a model and on radiated steam capacity, find out the key process parameters and its performance against quoted efficiency by the vendor. So this article was also published in the PR Chronicles. On the right hand side, I mentioned another article which is completely based on my work, that I was leading the commissioning. I was leading as a commissioning engineer for safe startup of this unit and provide training to the operation staff from process safety information collection to pre-startup safety review, from risk assessment to the salt solution development and cycle increment. I was responsible to handle all of this. Okay, so next is the commissioning of the first isomerization unit of Pakistan and its simulation model. I was the part of this team. As you can see that I've also proved the UOP rule of thumb that 1 weight % of benzene in the feed will raise the reactor temperatures by 11 degrees centigrade. So pre-startup activities as well as commissioning, I was leading night shift at the plant. Yeah, I was part of 2 major refinery turnarounds, which includes catalyst unloadings, loadings, regenerations, major equipment replacements like heat exchangers, columns, vessels, columns modifications, and revampings like tray replacements for increasing the gasoline uh, gas valve productions, and the management of change implementations. So it was really a great experience. One turnaround was conducted or happened in 2014, and the other one is in 2019. Okay, so last but not the least, process safety management activities. I've been continuously engaging in HAZOP of different process units, PSSR of all new facilities, one project related to the flare system loop addition to avoid back pressure line dislocation study. Uh, in this study, we have added an additional loops to avoid the back pressure line displacements. So for that, we have uh, done uh, a study on a Unison flare system, um, and the flue gas dispersion modeling, uh, operating procedure developments, incident investigations uh, using tripod beta method, PSM internal audit team member, and MOC handling. Uh, I have been working as an active PSM member during the audit. Thank you very much. Time was very short and could not explain all of my projects. So follow me on LinkedIn. Here's the link, and email me at this address. And thank you very much.
We will now move on to our next finalist. Here with us live from Dow Consumer Solutions, it's James Kenny. Over to you, James.
Okay, so can everyone see my presentation?
Yes.
Fantastic. Okay, so hi everyone, thank you for this opportunity today. My name is Andy Kenny, and today I'm going to be speaking with you about my early career experiences in the Dow Consumer Solutions business. So my first name is actually James, but I do go by my middle name, Andrew or Andy. I'm American, and I grew up in the sunny southwest of Chandler, Arizona. I now live in Midland, Michigan, where I'm a process research engineer in silicone elastomers, and I've been doing this role for about 5 years. My previous role was as a sealant commercialization engineer in Elizabethtown, Kentucky, and my hobbies include working on cars. You can see a truck that I've been working on restoring in the lower left-hand corner there, cooking, hiking, history, and traveling the globe. So I was an exchange student in Germany in high school, and there's a picture in the lower right of my wife and I in Germany for my host brother's wedding. So it's a great experience, and we try to get back well anywhere we can as often as possible. So anyways, back to my career. So this is just a quick overview. I began my career as a product development intern working on 3D printable silicones in the summer of 2014. It was a great experience. I was able to receive a patent at the end from the work that we did, and it was really my first foray into industrial R&D, and it was at that point that I knew that that was what I wanted to build a career doing. R&D is really my passion. I received my Bachelor of Science from Michigan Technological University in May of 2015, and that July I started at Dow as a process research engineer in the Dow Consumer Solutions business. So from 2015 to 2017, I developed expertise in the product and process technology, which we use in silicone rubber. So just kind of learning the technology, the ins and outs of everything, and I was able to apply this to continuous improvement as well as leading projects to expand the capacity of our silicone rubber processes. I also led a project to improve the safety of our hydrogen generating silicone rubber processes. And then 2018 to 2020 built on this experience that I gained by applying my skills further to develop most effective technology, or what we call MEP, for making silicone rubber compounds. And this supported an $11.5 million investment in Barry, Wales. We expanded our existing rubber plant with new improved process technology. And this was really the highlight of my career to this point. I love doing this, seeing everything from the very early scoping stages, developing the technology, installing the technology, starting it up, and now supplying customers. It's been a great experience, and I hope to do this much more in the future. So from 2018 to 2020, in 2020, I did complete an assignment as a commercialization engineer in Elizabethtown, Kentucky, again for silicone sealants. And then 2020 moving into 2021, and now have built on that work from 2018, 2020 in developing improved process technology for silicone rubber, and continue to work on that today. I also, before I move on to the next slide, did just want to emphasize that our silicone elastomers, so this includes our high temperature vulcanizing silicone rubber, as well as our room temperature vulcanizing silicone sealants, and many other silicone materials that we make, are very much product by process. So strong expertise in process R&D is important to our commercialization culture. I've had the pleasure of commercializing 13 new silicone products, mostly in silicone elastomers, and I look forward to doing this many more times in the future. Another passion of mine is, bringing new innovative products to our customers. So a little bit more about the consumer solutions business so that you can understand where we fit. We see ourselves as powered by a global, inclusive, customer-centric workforce that collaborates to deliver innovative, sustainable solutions. So to be this kind of effective team, agility in our R&D operations, as well as rapid speed of commercialization, are crucial to our ability to serve customers. If we can't work quickly, if we can't kind of change on the fly when we need to in order to answer whatever challenge we're facing in R&D, we're not going to be successful. Our business within Dow makes about $5 billion a year. We have 21 global manufacturing sites and 12 global R&D locations. We're focused on 6 different trends. You can see those in the middle there. 4 of those are circled in red. Those are the areas that I most affect, and so I figured I would point those out. Mobility and transportation is very important to our business in the form of what you see on the left there. So airbag coatings, fluid-resistant seals, and turbocharger hoses. Furthermore, I've been a part of a newer application in self-sealing tires that I wanted to discuss today, so I'll do a little bit of that on the next slide. Finally, in industrial and chemical processing, with silicones being highly insulating materials, we do supply materials to the oil and gas industry for use in subsea applications, and I'll also be discussing that today in a bit more detail. So now on to self-sealing tires. I'm really excited to talk about this project. I think it aims to meet a major trend in the industry, which is sustainability in the form of responsible production. So on our own end, as well as our customers. With silicones being such low surface tension materials, it can also be fine-tuned to cure when desired. Our materials really are perfect for this application. So this product will be internally applied by the tire manufacturer during manufacturing of the tire. In application with the end customer, it will serve to make transportation more sustainable by removing the need for a spare tire in the vehicle, and also by increasing the average life of a tire. This is possible by the fact that when a tire is punctured, the silicone material on the inside will wet out into the hole and prevent air from leaking out of the tire. You can see that in the 2 illustrations to the right. So the orange material in the bottom picture and the shiny black material in the right picture is our product applied to the inside of the tire. And then now, instead of getting a flat and likely ruining the tire while pulling to the side of the road and having to change to a spare, the tire will stay inflated and function and live on to the end of its life when it's finally worn out. My role in this project has spanned from making these materials at an R&D scale to support internal and customer qualification, to assisting with the design of new equipment to make this product in the plant, and finally, the startup and qualification of this new process equipment in manufacturing. Now on to some more fundamental chemical engineering work that I also wanted to highlight today. The next project really hits the mark on a couple other trends that we see in our industry in chemical engineering of digitalization and improving process safety, which I will explain. In this project, we wanted to develop a thermally insulating material that would function in applications where the industry is moving towards deeper and higher temperature oil wells. Although some non-silicone materials already exist in this performance space, we believe that by combining glass syntactic polyurethane, or GSPU, already used in lower temp subsea insulation service and supplied by Dow, as well as high consistency silicone rubber, or HDR, which is my area of expertise, we could supply a durable, lower cost, and more easily applied material than currently exists. So HDR, being highly thermally stable, provides an excellent inner layer that can be coated by industry-proven GSPU. Insulation in these applications is crucial because in the event of stop of oil flow, which can be for various reasons, inadequate insulation or failed insulation can allow the oil to cool excessively and precipitate out high boiler waxes, which can clog the process lines, requiring extensive downtime and causing potential safety issues by having to defoul using line pigs and other equipment. This is obviously very undesirable and poses a safety risk. So our solution was to use the molding equipment of the customer who was already using glass syntactic polyurethane for convenience and cost. So we wanted them to be able to kind of just take what they already had and use it for this new application. The idea was to apply the uncured HDR to the pipe and then overmold it with GSPU and their standard GSPU processing equipment. As the GSPU exothermed while it was curing, it would transfer heat into the HDR and cure it. This co-curing was also crucial for proper adhesion between the layers, and it would also make the process cost effective. So you can see the configuration I'm discussing in the illustration below. Because developing a process like this organically would require extensive trial and error, costly experimentation with the customer, we needed a way to rapidly test this concept and quickly make a go or no-go decision before investing a lot of resource. I believe computational fluid dynamics would be the perfect approach. We'd simulate both heat transfer between the pipe, HDR, and the GSPU layers to determine the ideal thicknesses for adequate insulation. It would also simulate the exotherm of that GSPU and the subsequent cure of the HDR. And here is what we found. So first of all, we modeled a system where high consistency silicone rubber had been applied around the industry standard steel pipe. The pipe was then placed in the GSPU mold. At that point, the GSPU was injected and the timer started on our model, where as it quickly exothermed and cured around the HDR covered pipe. With this model, we just demonstrated that full cure of the necessary layer thicknesses could be expected after 46 minutes. As the top illustrations show, you can see it at 34 minutes, about 50%, and then 46 minutes, we've got full cure, which is indicated by this red color. Again, middle layer in red is the HDR after full cure. We modeled the temperature profile while building the cure model. This is shown at the bottom and indicates that after 23 minutes, the temperature equilibrates at about 85 C in the mold. So we needed a temperature model in order to build this cure model, but we also wanted a temperature model so we could test how the material would perform and how that temperature would be striated over time in application as well at various oil temps. So what did this tell us? Well, first of all, it showed us that we had a viable application method as long as we could overcome other engineering challenges and as long as the molding time was acceptable to the customer. Furthermore, we were able to cut many months out of our R&D timeline by running many iterations in this model to determine the optimum conditions for success. So this is where modeling like CFD really shines. If we'd wanted to do this through trials with the customer, it would have been quite expensive, and we could potentially have wasted months of expensive R&D and customer resources with little or no gain if the project didn't pan out. Or even if it did, it still would have been much more expensive. So I think this was a perfect example of innovating through digitalization to streamline our work as chemical engineers. Now I'm going to wrap things up. As you can probably tell, I do love what I get to do with Dow. All my friends, all my colleagues know that I nerd out every day with the different things I'm working on. We have so many products and so many different applications and industries. I'm constantly excited by my day-to-day work. This is an amazing place to work. I'm constantly thankful for how fortunate I am to be an engineer in general and also to work in this industry and do the specific role that I do in process R&D. So my careers span continuous improvement, optimization, process development, and alongside all of that, commercialization. My expertise has been largely focused in reinforced silicone elastomers, but in the course of my work, I've also broadened this to organic elastomers in various projects, polyurethanes, and 3D printable silicone resins. So the projects I've worked on have been largely centered around the three critical trends that I've discussed in this presentation. So the first one being responsible and sustainable production via the Selfstealing tire project, as well as the new plant investment in more efficient process technology in Barry, Wales. digitalization of our chemical engineering field via CFD modeling. So I've used this to a very large extent in the project that I mentioned, as well as in many other projects. It's an incredibly useful tool. And I've presented some of this work in other forums too, even outside of the project I mentioned today. And then finally, improving process safety, both internally and externally via my project to improve hydrogen safety in our hydrogen generating rubber processes, as well as the subsea oil and gas insulation project, where our product can ensure sustainable and safe extraction of oil to meet market needs in the energy as well as chemical feedstock sectors. So it was an honor for me to speak with all of you today, and I wanted to really thank you for your time.
Thank you very much for that presentation. If you have a question, please type it into the question box now. And whilst I give you a moment on that, don't forget there are more IChemE Award webinars coming up tomorrow. You can find more by visiting icheme.org/global awards. We don't appear to have any questions, so thank you again very much. We're going to move on to our third finalist of the day. It's Bashir Altakan from Saudi Aramco. We can't hear you, Bashir. Maybe you're muted.
Okay, can you hear me now?
Yes, we can hear you now. Thank you.
All right. Good afternoon, everyone. My name is Bashir Altakan. It is, in fact, a great honor and privilege to be selected among the finalists for this year. So I'd like to thank the Institution of Chemical Engineers for giving us this platform to present our work and present a flavor of several different projects that I've worked on that tap into addressing certain industrial challenges, particularly for the oil and gas industry. Before I get started, just to give you a little bit of a background about myself. So I'm originally from Riyadh, Saudi Arabia. I obtained my dual bachelor degrees in chemical engineering and economics in 2016. Shortly after graduation, I joined Saudi Aramco to work on production technology research. And I've also done rotational assignments in several major oil fields in Saudi Arabia to identify the areas needed for R&D developments. Recently, I just obtained my master's in material science engineering from Cornell University, and I'm currently pursuing my PhD in MSc as well. So my presentation today will basically cover three different areas. I will first share the low viscosity acid system that was successfully transformed from a lab scale into a deployable technology in the field. Moving on to a multifunctional nanoparticle platform that I worked on in Professor J. Ellis as part of my master's that was successfully, that were recently published and has tremendous potential for a field application. Last but not least, I will briefly talk about some industrial outreach efforts that I've been a part of that go beyond research and lab developments. So let us first start talking about the low viscosity acid system. What was the interest for us to develop a low viscosity fluid in the stimulation of carbonate reservoirs? First, it is worth mentioning that carbonate reservoirs contain a significant portion of oil and gas resources worldwide. And the mineralogy of these formations, in fact, very heterogeneous. So they contain calcite and dolomite, sometimes a combination of both. So acid stimulation treatments have been proven to be very effective in enhancing production from these particular formations because they can solubilize and dissolve the calcium and magnesium-based carbonates. Therefore, it will provide highly conductive channels for hydrocarbon to flow. So several acid platforms have been explored in that regard with one conditional property. So the acid needs to have a strong retardation. In other words, it needs to have a delayed reaction when encountered with the rock to allow the treatment to propagate into deeper reservoir zones. So in that regard, emulsified acid systems have been the dominant class in these particular treatments because you can achieve emulsification or retardation by emulsifying hydrochloric acid with diesel, for example. That will provide the temporary barrier for the acid interaction with the rock itself. The problem with conventional emulsified acids is that they have a very high apparent viscosity, so above 30 cp. This will result in a high frictional pressure drop that would also impede the pumping efficiency. And also because it's a two-phase system, the mixing condition in the lab scale does not necessarily transfer at the field scale. So I've been in several occasions in the field where these batch mixers are utilized, and there are a lot of quality control issues when it comes to demulsification and phase separation. So in fact, you would induce damage as opposed to enhance production. So the idea that we propose is that we can in fact achieve retardation without the need for utilizing polymers or oil. And this can be done by mixing hydrochloric acid with other soluble organic acids that will be able to reduce the free water available in the system and control the proton diffusion to the rock itself. So this in fact has a very low apparent viscosity for CP at ambient conditions. It has a high dissolving power comparable to conventional systems, but it can also be readily mixed on the fly because it's a one-phase fluid. So the pictures that you can see on the right here are computed tomography scans or CT scan of an actual reservoir core that was core flooded with the injected treatment. So the top image is for hydrochloric acid. You can see that it is spent at the face inlet. Most of the treatment was spent early on in the injection process. Whereas for the low viscosity acid system, we have a more uniform and a dominant wormhole propagation with a minimal branching in phase dissolution. So this was successfully published in the patent, and we were able to also deploy it in the field, several gas fields in Saudi Arabia, in fact, that showed enhanced efficiency and cost savings as well when it comes to pumping operations. So moving on to a different scope of work at the nanoscale in Professor Gianelli's group, supported by King Fahd University of Petroleum and Minerals, where we developed two polymeric nanoparticle platforms. One is designed for acid, foam, and surfactant in situ release, and the other is for the target delivery of subsurface applications to enhance oil production. So let us start by the first system. Enhanced oil recovery methods, in fact, capitalize and rely heavily on surfactant assisted treatments to basically mobilize the residual oil, as they are very effective in reducing the interfacial tension between oil and water. The problem with surfactant flooding is that they are economically and operationally challenging. So they can result in premature absorption, meaning that a lot of the injected treatment does not make it further into the reservoir because they prematurely absorb to the rock surface. Pore blockage has also been observed because of the additive chemicals to stabilize these active agents in harsh reservoir conditions. So the idea we propose here is that we can have a nanoparticle carrier that is small enough to navigate through the porous media. It will be able to release surfactants in a very slow and controlled fashion. Therefore, we will ensure that as much surfactants can be delivered to deeper reservoir zones. So the results that were published recently show that we were able to achieve this by having a pendant asteroid group that will be able to undergo hydrolysis to release the desired surfactant. And the added benefit of that, we can have carboxylic acid, in fact, produced in addition to CO2 foam, which has an added benefit to enhance oil production. Also, the hydrolysis calculations that we did prove that these surfactants have a very slow and controlled behavior, even in an accelerated hydrolysis in an alkaline mixture, so at high temperature as well, similar to the reservoir environment. What was particularly interesting is assessing the surfactancy of these nanoparticles. So these are confocal microscopy images of emulsions prepared between oil and water. So oil is represented in the blue phase in this case. Typical oil-water emulsions will phase separate. They're not very stable, but whenever we had the added nanoparticles that add this a little bit of surfactancy, we can clearly see that they assemble at the oil-water interface, stabilize emulsions that are much smaller in size and much more stable. The other platform we also developed was designing nanocarriers that will be able to, we can load them with whatever active agents we want to deliver for subsurface treatments, but we can also self-functionalize them to allow them to be selectively deliver and specifically target subsurface oil or the formation rock. So the images on the left here are SEM images that show these nanoparticles are about 100 nanometer in size. And when we load them with Nile red, which is a fluorescent dye, and we took confocal microscopy images on the A, B, and C micrographs on the right here, you can clearly see that these nanoparticles, in fact, assemble at the oil-water interface. They are able to identify the oil phase and partition at that particular interface. So the control image taken in D in this case are for the particles that were not surface functionalized, just to show an example of how this can be in fact used for a more efficient and cost-effective delivery of active agents for subsurface applications. So switching from science to some industrial outreach efforts that I've been a part of. So I've been very fortunate to take part in multiple professional and social organizations. I'm currently the corporate co-chair at Cornell Graduate Society of Women Engineers, basically reaching out to industry representatives to secure funding and arrange for essential networking opportunities for women in STEM. So we're able to send our members to the local and national SWE conferences to present their work. We also arrange for resume reviews with the companies to ensure that our members are ready for the recruiting when it happens in the career fair. So also in Saudi Arabia, I've led the event planning and coordination team of technical programs as part of the Society of Petroleum Engineer, which is the largest section outside of North America. And we also arrange for lectures and panel discussion between industry, government, and academic organizations to facilitate interdisciplinary discussions and also tackle some of the technical as well as the diversity issues in the petroleum industry. I'm also acting as the vice president for the Saudi student clubs at Cornell to arrange for professional development opportunities and also arrange for industry social events now. So with that, I come to the conclusion of my presentation. Again, I would like to thank the Institution of Chemical Engineers for giving me this opportunity. I would like to thank Saudi Aramco and my sponsoring organization, the Expect Advanced Research Center, for their tremendous support throughout my early career as well as throughout my graduate study, and Cornell University as well, and King Fahd University of Petroleum and Minerals for their generous funding in the research projects. I would be more than happy to take any questions that you have.
Thank you, Bashir. We'll once again pause for questions. So you know the drill by now. Please type your questions into the questions box. And whilst we wait for that, if you've been suitably inspired by today's presentations, it might be time to start thinking about your own awards entry for next year. Keep an eye on the IChemE Awards website for more details, but we plan to open for entries in early March 2022. Thank you again, Bashir. We don't have any questions, so we'll have still 3 more contenders to hear from before we announce our award winner. So let me introduce our next speaker. Please welcome Michael Turley from Shell.
Hi, thanks. So my name's Michael Turley, calling from Amsterdam in the Netherlands. And first of all, I wanted to say thank you very much to the IChemE for the nomination. It's already amazing to be able to get this far. And a big thank you already to my colleagues at Shell, to my line manager, Robert Schauvenaar, Tigo Goswami, my mentor, who've helped me get to this amazing moment. So I assume everyone's read the cautionary note. What I want to quickly do in 5 to 10 minutes is give you a background of who I am and how I've gotten to this point, a little bit about the volunteering work I do, and then talk briefly about what my main focus is at the moment, so the topic of blue hydrogen. And then finally finish with some reflections. So I've always had an interest in science as far back as I can remember. And I even managed to dig up a nice photo from 2001 showing my first chemistry set. So always been interested. And I took that through with me. And I did well at school, and my careers advisor said, hey, have you thought about doing chemical engineering? It's basically science on a big scale. Felt fantastic. So I signed up to go to the University of Sheffield to study a Masters of Chemical Engineering, and really fell in love with chemical engineering when I had my first taste of industrial experience, working for ConocoPhillips in the UK. After that, I went back to university very motivated to do well, finished with a first-class master's, and then was fortunate enough to get a job working for Shell, relocating to Amsterdam in the Netherlands. And this was an amazing first opportunity working as a gas processing engineer. So that role was all about designing gas processing equipment such as CO2 capture systems, and really developing those chemical engineering skills from university. So developing things like process models, learning the skills how to develop size equipment, learning about process safety, and how to apply process control. After I finished the graduate scheme at Shell, I moved to Malaysia to work as a hydrogen technologist. And this was a great transition because I moved from the design phase into actually operating a real production unit. And here it was hydrogen, and hydrogen obviously a very exciting place to work. At the end of my time in Malaysia, there was an opportunity which appeared back in Amsterdam, and my line manager said, do you want to come back and have a look into blue hydrogen? And as I'll touch into this later, blue hydrogen is a really exciting developing field, and I jumped at the opportunity to take the role. But before I go into blue hydrogen, I'll set the background to that in a moment. But just in the background as well, besides my professional work, I really enjoy giving something back, especially now I've got a bit more experience. So I really enjoy going back to my university and delivering lectures or supporting students, such as students who are thinking about doing an engineering course or helping second and third year students with their engineering projects. As well, I'm really motivated by clean energy, and I like to connect with different engineers from different fields, and that's why I volunteer with the Institute of Chemical Engineers as a committee member for the Clean Energy Special Interest Group. Now, if I move on to my main focus that I've been working on since early 2020 about blue hydrogen, I'd like to first set the scene about, well, what actually is blue hydrogen. You might hear a lot of it in the newspapers. Well, basically, we talk about three main colors to do with hydrogen, and the colors just refer to the way in which it's manufactured, so not the actual gas itself. We have gray hydrogen, which accounts for more than 95% of global hydrogen production today. And that's simply taking a fossil fuel feedstock, effectively splitting it into hydrogen and carbon dioxide. And usually the carbon dioxide is vented. Then you have green hydrogen, which is taking green electrons, so renewable electricity from wind or solar, and using that to split water. Here, the only byproduct you have is oxygen instead of the CO2. Then we have blue hydrogen, which is somewhere in the middle. It's taking a hydrocarbon feedstock, splitting it, but instead of venting the CO2, we capture it and store it. Now, why do we talk about blue hydrogen? Well, the world is going to need a lot more hydrogen in the future. It's going to be critical for us meeting the Paris Agreement. Hydrogen is an incredibly versatile molecule. You can use it for a range of applications such as industrial decarbonization, heavy vehicles such as trucking, ships, where batteries would be too heavy, and also other options such as steel, cement, and possibly blending into the natural gas grid. If you look at what the International Energy Agency is predicting, they say that blue hydrogen production, which is this yellow block on the chart on the left, has to increase by 100-fold by 2050. That's driven by the fact that if you compare the prices of the different hydrogen solutions today, so green, gray, and blue, green is still very expensive. It will come down in price as electrolyzers mature and we get economies of scale, but still blue is significantly cheaper and will help us meet the energy transition by deploying technology today at a low price. When I came back, I worked with Robert, my mentor Tigo, and a wide range of engineers from Shell, and we said, look, we want to get into blue hydrogen, and because Shell has a rich history of CO2 capture and storage, and it also has a rich history of producing hydrogen through its gasification technology. And we said, how do we get those two different technologies together, and how do we integrate them to make a solution which is cost effective? And for that, we used bread and butter chemical engineering. So really the skills you learn from university. So we went through, we developed concepts, we developed block schemes, we ran simulation models, we looked at the utility balances, we did cost estimates, and eventually we came to a solution which we got really excited about. And that's what we're calling the Shell Blue Hydrogen process. To give you a little bit of background about what it is, you basically have an SGP reactor at the front end, a gasification reactor, You feed in your fossil fuel and you produce a syngas, or a mixture of carbon monoxide and hydrogen. You cool that down. You further convert the carbon monoxide using a water gas shift. Then you capture all of the CO2 with your Adip Ultra CO2 capture units. Then the hydrogen, we purify it some more before finally shipping it off to the final consumer. There are a lot of advantages with this approach, but in the time, I just want to touch on two main advantages. One is that the gasification process is non-catalytic. That means the process is more robust to any feed contaminants. That makes it ideal for things like dirty feed gases, such as refinery fuel gases. The second big advantage is that it's proven to operate at much higher pressures than conventional blue hydrogen technologies. That's important because a higher pressure means it's a lot easier to capture your carbon dioxide. And then you're able to capture it at a much higher efficient pressure, and you can regenerate it so you can separate it at a much higher pressure. That gives you big savings in terms of your final CO2 compression duty. So we released this in the mid of 2020, extremely excited. And the key advantages it can bring is, we see it can bring substantial savings in terms of capital expenditure, your plant's OPEX, the cost of your hydrogen as well. I don't have time to go into all of the details, but I've shared material at the end of the presentation pack. But I wanted to use the remainder of my short time to basically reflect on the whole process of my background and how we've got into this blue hydrogen stage. I think it goes to show that chemical engineers have a hugely important role coming as we go through the energy transition. We're well equipped with the skills to address some of the big challenges. And I think it's an incredible opportunity, incredibly exciting time. And I fully encourage new young engineers as well to consider taking up chemical engineering. Finally, I'd like to re-thank my colleagues at Shell, because they've given me the huge opportunities to develop, and also the huge opportunity to work in Shell Blue Hydrogen. And finally, if you do want more information on blue hydrogen, because there's a lot of good stuff to learn in this space, then you can find a recording of our webinar. Just Google Shell Blue Hydrogen process, and you can watch our 30-minute webinar to give you more of a background. And with that, I'd like to finish my presentation and welcome any questions, and best of luck to all of the other finalists. Thank you.
Thank you very much, Michael. We'll now move to Q&A. So if you have a question, please type it into the questions box as usual. I will give you a moment for that. We don't have any questions, so thank you very much again, Michael. And now we'll move on to our next presentation. Please welcome Donald Alexander Barden from BM Group.
Thank you, Mara, and thank you, Charlotte, and hello to everyone listening. Before I begin, I just want to thank the Institute of Chemical Engineers and the judging panel for giving me the opportunity to present my work. My name is Donald Alexander Barden, and today I'm going to talk to you about my career in the pharmaceutical industry. So everyone here has been affected by COVID. Most people here would have had the vaccine. It has never been more important to achieve fast drug delivery. The world has been exposed to the challenge of drug delivery, with challenges of cost and challenges of production. When we look at the map here in front of us, we can see that most countries have received their vaccination, but there are still few countries that have yet to receive sufficient vaccination. Now, that's the challenge I want to talk to you about today, is that challenge of drug delivery. Every sort of drug has the three industrial challenges. They all have the challenge of cost, waste, and production. If we're able to reduce the cost, if we're able to reduce the waste, and if we're able to increase the production, we're able to improve the accessibility to these treatments. And if these treatments are cheaper, then we are able to achieve a more fairer accessibility to these treatments. These industrial challenges were highlighted last month in the Chemical Engineer. This was in the September edition, where these new modalities like cell and gene therapies, they cost greater than 10 times the price of gold per kilo to produce. They produce 10 tons of waste for every kilo of product, and they produce often low manufacturing volumes. Now, these low volumes refer to clinical trials, and they refer to treatments such as cell and gene therapies, which offer a treatment for rare diseases, which are absolutely essential. But in nature, they're hard to scale up. If we're able to produce facilities that are multi-product, we are able to produce treatments for multiple diseases and therefore get treatments to more people. So I've had a variety of experience ranging from design work and also as a commissioning engineer working on these biological facilities, but I want to highlight 2 areas of my contribution towards this industrial challenge with you today. And then I'll summarize at the end by going over this contribution and giving you my goal for the future. So my most recent contribution to this challenge is my work on the CAR-T facility. This was a design of a facility to be built in Belgium. It's going to be built in Belgium in 2023 for a leading pharmaceutical client. So this is a cell and gene therapy facility, and the treatment is for myeloma. Myeloma is a blood cancer, and it kills 33,000 people per year in Europe. This facility produces 4,000 treatments per year. Now, this is a one-off treatment for patients, and it's potentially life-saving. This facility is a multi-product facility, so it's capable of producing 2 separate treatments simultaneously. And that is what helps it achieve that high capacity of 4,000 patients. So there we have our high capacity, but if we think back to our challenges, if we are also able to reduce our cost and reduce our waste, we're able to make this treatment more accessible to more people. So I just want to highlight my own achievements on this design. So I delivered the complete and safe design of the facility. So this included the sizing of utilities. This facility uses a lot of liquid nitrogen. So it involved the sizing of a whole liquid nitrogen system, but it also required the due diligence for safety on the design. So this involved doing oxygen depletion assessments, doing the detailed calculations to make sure that the areas that could be affected by a liquid nitrogen leak have sufficient ventilation. I also want to highlight my undertaking of specialist witness training. So witness is a simulation software, discrete simulation software tool. And I use that tool to build a digital model of the entire facility. So on the right, we'll see a video playing. So this is a top-down view of the layout of the facility. This is just a small example of the facility. So the moving parts that we see, those are operators moving through the locker room into the facility. So this small example just kind of shows us how we can use this tool to monitor operators as they move through the facility. In this case, in the locker room, we can monitor the gowns that they use. So this is a biosafety level facility that uses a lot of gowning materials, so we can reach a high grade of protection. So we can monitor with the simulation tool how much gowning that they're using, and also once they're returning after a shift changeover and they come back out, they will degown, and those gowns now become waste, and we can monitor how much waste we have. So this simulation tool, I've used this to model the entire facility. So each process suite I've modeled, and you can, I've used this model to track the patient blood samples as they move through the facility. So it's a very manual process and it uses a lot of consumables. So by doing this model, I was able to make sure that you could identify the bottlenecks where the materials were needed to make sure that the patient sample moved through the facility without delay. It's a 10-day process and it's critical that it gets back to the patient. Also, the operators are critical because it's such a manual process that uses a lot of benchtop equipment. It's essential that the operators can get in and out of the suites without delay and without bottleneck. So this was a success. We were then awarded the design of a similar facility to be built in Belgium also by the same client. And I just want to highlight the contribution that this makes to our goal of accessible therapies. So down the bottom, we highlight this is an example of delivering a design of high capacity. And I ensured that this facility was able to achieve a high capacity through the simulation model, okay? By looking at areas of bottlenecks, if there's any areas of delay, and putting in and implementing solutions to make sure that those bottlenecks are mitigated. Also using this simulation tool to reduce equipment, so identifying opportunities potentially to share equipment or potentially to remove equipment that's redundant and you might not need. So this reduces costs and reduces wastes. Okay, so when we think back to our challenges of reducing cost, waste, and increased capacity, this makes this treatment more accessible by doing so, and it gets it to people that need it. So now I'm going to go on to my second contribution of the Industry 4 contribution. So Industry 4 describes the next generation of technologies that's used in industry. And PM Group have a technology initiative within our group that looks at these technologies, how they can be used within PM Group to improve our own services, but also on our clients' services, okay, and on their facilities. So when we're designing facilities, making sure that these are implemented. So I coordinate a group of global pharmaceutical SMEs, so SMEs being subject matter experts, and we look at these technologies and raise awareness of these technologies. So on the right, there's a picture of me there in the ISP exhibition in 2019. This was at the Old Trafford Stadium in Manchester. So it was a fantastic experience. There I showcased what was the factory of the future. So this was our culmination of all of these technologies included in one design to showcase the benefits of all of these technologies. An example of these technologies I'm showing on the left in bold. So you've got augmented reality. So these are augmented reality goggles to be used during construction for construction verification. Also simulation. So we've used the previous example of simulation to build a new facility, but you can use simulation tools to help existing facilities. So if you build a direct copy in the virtual space of an existing facility, you can then implement change to that model and you can simulate any of these changes. So if you want to input a new process or increase capacity, you can do that virtually and you can see any problems that you may face, any potential bottlenecking, any potential issues with supply, and you can mitigate those problems without doing it in real life and inducing that cost. So I just want to highlight my own achievements within this group. So the first one is I delivered and developed an app, what's called the PM Group 4.0 app. And I just want to show you an example on the right there of the app. So this is just a screenshot of me showcasing this app, which showcases all of the technologies involved in Industry 4. So we've got robotics there in the middle, cybersecurity, cloud computing. We touched on augmented reality and simulation. So what this app does is we can explore these technologies, dig deeper into them and see what values they are holding and what's the potential of these technologies and how they can be used in the real world use cases, so you can show the potential of these technologies. And these are ultimately to reduce the cost of facilities, reduce the waste, and increase the capacity. So this screenshot I've just got on the right there, that's me presenting to the PM Group directors. So this is me showcasing the app. It's since been approved and it's currently in development to be rolled out within the company, and we'll roll it out to industry later. This is me also presenting the path for Industry 4, our direction within the team, so that would be approved as well. And just my final achievement here, I've been the project manager for the technology initiative for 3 years. It's been a fantastic experience. I work with fantastic pharmaceutical SMEs, which have a wealth of knowledge who I learn from, and it's an absolute fantastic experience. So in summary, this is my final slide. So we touched on the industry challenges. You got your cost, your waste, and production. So hopefully you can take that away with you today. And then my contribution towards those challenges. So it was just 2 examples that I've highlighted there. So the first one being the CAR-T facility, where we reduce costs, reduce waste, which in turn reduces environmental impact. And I verified the design of a multi-product facility. Okay, and this facility is capable of achieving high capacity of 4,000 patients per year. So that helps our goal of making this treatment achievable and accessible to more people. The second contribution was within Industry 4 and my role in technology development. This looks at new ways of working, and this is new ways of working better. It's not about working more, it's about working better, which gives you faster drug delivery. So my contributions reflect my tasks, maybe day to day in design work, of trying to optimize client facilities. I've also been involved in commissioning these fantastic new facilities, which have been a great experience for me in the foundation of my career. But at the end of the day, my goal is to improve access to these life-saving treatments by fixing these industry challenges or working against these industrial challenges. We can make these treatments more accessible to everyone. Okay, so thank you very much. It's been a fantastic experience. Thank you for the opportunity. I'd been privileged to work on these fantastic projects, and I'm privileged to present to you today. And I'm happy to answer any questions about the industry challenges or any of my experience or my contributions. Thank you very much.
Thank you very much, Donald. Once again, we will pause for a moment and give you a chance to submit a question in the questions box. We don't appear to have any questions, so thank you very much again, Donald. And
Thank you.
it's time now to move on. We have reached our last presentation of the day. Please welcome Ed Ali El from Saudi Aramco.
Hello, can you hear me?
Yes, we can hear you.
Loud and clear. Okay. Can you see my presentation?
Yes, we can.
All right. So if you can hear me clearly, I think my presentation is appearing now on the screen. So at the beginning, it's really an honor to be here among my amazing colleagues. I heard all the presentations. It's really amazing to be with this special group. And for this, we would like to thank the IChemE Global Awards for this amazing event. My name is Iyad Ali Al Ali, and I'm from Saudi Arabia, and I work with Saudi Aramco. At the beginning of my presentation, I would like to take you on a short trip of just a little bit about myself. So I am from a beautiful town. It's called Al Gara, and it's from Saudi Arabia. And it has a beautiful mountain surrounded by thousands of palm trees. In that little town in 2010, with my graduation from high school, my dream was actually to study abroad and gather this experience of working and studying in a multicultural environment. So I was sponsored by Saudi Aramco in 2010 to get my bachelor degree in petroleum engineering. So I had the opportunity to travel to the United States of America, where I spent 4 years there to get my petroleum engineering degree, and graduated in 2015 from the University of Oklahoma. So when I came back to Saudi by then, after graduating, I started my career journey in the energy industry, specifically in oil and gas upstream business line. And my job role was as a petroleum engineer with the Saudi Aramco XPEC Advanced Research Center. Now, this center actually is focusing on upstream research in many different areas, such as drilling, production, reservoir, geology, and geophysics. And specifically, I work with the production technology team, focusing on productivity enhancement research area for oil and gas wells. Our team works in developing chemical treatments that are pumped downhole to the rock reservoir, and that will enhance the hydrocarbon production to the surface up to the downstream. So this is the first step where I had my engagement actually in the business line of the chemistry and the chemical engineering, where we handle the chemicals in the lab and develop these recipes for the field. So to be excellent in this work, I had my technical rotation, and I started with gas reservoir engineering, where I was working as planning and designing and constructing these wells in the reservoir, also planning all the treatments that are needed, and selecting which reservoirs we should produce from the field. After this assignment for 1 year, I also went for another assignment in the field, actually having a hands-on experience with the well production as a gas production engineer. And here I was developing the well chemistries that are necessary for the treatments for the downhole reservoir. And that was the main job for this assignment for 1 year. So we have many wells that we drill, and we have to treat each one specifically for its design and for its target rate. So this will also include all the work that I do in monitoring the wells for production and producing these oil and gas wells all the way to the plants. So here I will start with some specific challenges that we receive from the field. Being with research, we bring some challenges from the field, and then we build a project related to these challenges. So for this challenge, we have a downhole stimulation for the reservoir. And for this, we have a reservoir treatment, a reservoir stimulation chemicals that we pump in downhole. So these treatments are actually important to stimulate the carbonate rocks. And these carbonate rocks has to be stimulated so the cavities are going to be opened and the hydrocarbon will be flowed up to surface. So usually we use hydrochloric acid for stimulation, but we know that acid reaction is really fast and it can dissolve the calcium carbonate very quickly. So for deeper treatment, the industry has been using slow reacting acid, which is the emulsified acid. Now, the emulsified acid has been used widely and globally everywhere. It consists of 30% of diesel and 70% of hydrochloric acid. Now, the challenge with the emulsified acid that it poses a long mixing time. It somehow has emulsion instability, especially with high temperature reservoirs. Our reservoirs here sometimes reach a temperature of 300 Fahrenheit, which is really high for these chemicals to be stable in the emulsion. And also we require a high pumping rate, but due to the emulsion construction, it has a high pressure when we pump it to the field. So the solution that our team came up with, and I was working with them in the implementation, was a low viscosity acid system. Now, this is a new technology that is developed in the lab. And now my role is becoming more significant at this step to take this technology for feed validation step and actually use it for multiple times. Here, I lead the engineering design, the chemical design and handling, the chemical shipment, the chemical mixing design and procedures, and actually going to field and witness the actual pumping of the chemicals in the job. So you can think about this as a lab test, but is in a really huge scale. And we do this in iterations. We do this for multiple wells, for multiple tests, where I get the feedback from the field, I collect all the information, and I get back to the scientists where we have to work and modify the recipes and also optimize it for another job. This is all happening before the full deployment and before approving the chemical for our operations in the field. Another challenge that we have in the field as well, that's another example of the projects that we work on in the research, is associated with gas flowback challenges. And we know that gas hydrates can form inside the flowback pipes. This is definitely happening because of the difference in temperature and pressure. It happens in our region when we get closer to the winter times, and these hydrates are dropping inside the pipeline. Now, those gas hydrates are usually treated with methanol, and it's used for treatments for these type of conditions. However, the methanol has a low flash point temperature, and we sometimes this brings huge challenges to us. These hydrates first, they have a huge challenge in blocking these pipes, and that could lead to a dangerous situation where the pipes could be blown out or the production can be stopped. So the challenge is with the methanol that is usually used in most of these scenarios, that is highly flammable, and especially in our region where sometimes the temperature goes to 50 degrees Fahrenheit. Our temperature here in the area in Saudi Arabia can go to 50 degrees Celsius. Actually, it's really hot in the summer, and now we're getting to winter. And during these days, the hydrates are forming inside the pipeline. So when they use methanol, it's really difficult to handle this methanol in the field. For transportation, we have very remote well operation in the field. Some of our wells are hundreds of kilometers away from the storage locations. So this is really hazardous chemical to be transported and to be shipped, especially during summer. So our research team and our team in Dhahran, and also we have research centers in Houston as well. We developed an aqueous gas hydrate dissolver, which replaces the methanol for our operations. So again, such chemical requires different mixing, different designing, and different pumping in the flow line. So this is where I come, and I had my significant contribution to the projects, where I go to the field, look at the pumping requirements, see the flowback designs, and getting in touch with all the service companies that are working there to pump this amazing fluid, which is a water-based, and it's safe to be stored and shipped, and it's highly effective. So this is my examples of the work that we do among different types of work that we have in the research team. We focus mainly on chemical treatments. These are two main examples, but also we have a portfolio of projects that are short-term and long-term projects as well. So for new technologies, we're working to develop more effective solutions to our fields. And most of them are related to chemical treatments, as I mentioned, for enhancing the productivity of these wells. So my job actually is to link the research arm with the field arm. And I'm depending on my technical and engineering skills in addition to my field experience as well. It is an important role for implementing our ideas and also for advancing the industry towards a better solution and also better operations in the field. Actually, it's a great pleasure for me working in this position, especially having all the contacting between the scientists and the engineers in the field. And it's really an interesting position that I find myself in. So I recently joined the technology deployment and commercialization team, which focuses on field tests and validation. And this is really complementing my work with the technologies deployment in the field. And also we work on technology implementation and deployment, where we have plans for each technology, how to be implemented in the field, what are the requirements to do there, and what are the outcomes that we expect from each technology. Also, we are linked with the business line for technology commercializations for products that we intend to invent here in Saudi Aramco and then put them in the commercialization line and have them commercialized internally or globally. And also, with all that, I'm focusing on process enhancement for these field trials and technology deployments. And that also led me to be very ambitious to continue my development. So I'm very keen to continue my development in this area. I'm actually studying Master in Sustainable and Renewable Energy. And this actually is a next step for me because I'm looking forward to be part of the energy sustainability projects and also aim to incorporate some sustainable and renewable energy solutions in oil and gas operations. These topics are really interesting to me, especially working with a great research institution like the IChemE Advanced Research Center and being part of a great company such as Saudi Aramco, where we definitely look for sustainable solutions for our energy industry. So on the other side of the technical work, I have also other activities with my company. We had an environmental project where we planted 600 trees. This is a great project for us here in Saudi because sometimes the summer temperature reach up to 50 degrees Celsius, as I explained. So for this unique project, where we had is a new technology, which is the SandX, which is a sand that you put on top of the ground, and it preserves the water from evaporation from underneath it. So you have underground water irrigation system where you can plant these trees remotely away and next to the Aramco facilities. I'm also involved with other professional activities, especially for young engineers. I like the section where I contribute with my experience to the young engineers coming to the business line. I was also a co-organizer for the Society of Petroleum Engineers Young Technical Symposium in 2019, where we hosted 600 students, many webinars and many technical classes, and that also benefits the new students around us in the region of Saudi Arabia. Also, in the outside of the professional world, I get a lot of energy from working with my community. And we have done many projects for the local organizations during many occasions in my hometown. And also one of the most influential volunteering opportunities was for us performing graduation ceremonies actually for students and present them with multiple STEM-related topics. We are a great team of professionals that we wanted to share our experiences with them and engage these young students before they go and enroll for the companies in the industry. Also, talking about my hobbies, I'm really skilled in sound and projection management. We have done many projects, and actually a few of them are amazing on the level of Saudi Arabia. This is the Saudi Film Festival in 2020 actually, where we use the projection, and I'm really skilled in this one. I really like this field. It gives me more energy to come back to work. And last but not least, and the closest one to me, is the activities in sports. I'm volunteering as the sports strategy leader and the youth handball team's manager for my hometown sports club, Al Gara Club. And here my work is essentially developing a steady income for the club, and my engagement with my teammates, and also my experience with my amazing coach gives me great momentum actually to come back to work every day and be motivated to work for successful projects in the work as well. So it's a continuous cycle where I have my work and my high activities in the industry and in the academia and also in the field, coupled also with my other side of the day, which is my amazing activities outside work, where I have them back to back supporting each other. Before I conclude, I would like just to mention that I'm really happy to be close to the engineering part of these projects, especially to the chemical engineering part. I didn't find myself going to this path, but however, I was really great in grasping the chemical engineering concepts, especially when I go to field. And I developed this experience with the scientists that I have here in IChemE. So I really would like to thank my teammates here for developing my skills in the chemical engineering, and also the global research centers for providing us with good technologies to be implemented in the field. So thank you so much for listening to this presentation. At the end, I would like to thank again the Institution of Chemical Engineers for this amazing and special opportunity, and thank you for listening.
Thank you, Ed. So for the final time today, we'll pause for questions. If you have a question, now is the time to write it into the questions box. So no questions, Ed. Thanks very much again. We have reached the moment that we've all been waiting for. It's time to find out the winner of the IChemE Young Industrialist Award, sponsored by Selfstealing Limited. Before we do that, I'd like to thank all our finalists for joining us today and for taking the time to share more details about the fine work. All of them would be worthy winners, but there can be only one. Let's start by announcing our highly commended finalists, and they are Bashir Aldakan and Ed Ali Alali. Well done to both of you. Congratulations. But now it's time to announce the award winner. Ladies and gentlemen, the winner of the IChemE Young Industrialist Award, sponsored by Selfstealing Limited, is Michael Turley. So congratulations, Michael. How can you tell us, how does it feel to be an IChemE Award winner?
Yeah, really surprised because listening to the quality of the presentations of everyone else, I think congratulations to everyone else as well. The broad range of applications everyone is working on and the work they're doing for society is all absolutely incredible. So no, it's really humbling. And so I'd like to thank again Shell for the opportunities, my line manager Robert, my mentors Tigo, and finally I'd like to use this award then to inspire the next generation of engineers, especially when I go to the universities, to present. So thank you very much, and also to the IChemE.
Well, congratulations once again, and thank you to everyone for joining us today, especially our finalists, and a big thank you also to our sponsor, Selfstealing Limited. And that's all for today. We'll be back tomorrow to announce our Young Researcher of the Year. But until then, it's time to say goodbye, and thank you very much for joining us. Thank you. Bye-bye.